now going to talk about how the solar system formed, or at least how we believe the solar system formed. Obviously, nobody was there when it occurred. So what do we have to do? We have to look at other stars in our galaxy that are forming right now and see if it matches what we find in our solar system. And we look at the evidence we see in our solar system for how the solar system was formed. So the view is that we formed, and we see stars forming right now, in these things called giant molecular clouds. And these giant molecular clouds are clouds of gas and dust in the disk of the Milky Way galaxy. And something in there has to trigger those stars and clouds to collapse. And once they collapse, all that gas and dust starts falling together. Then the more mass you get, then the greater the gravity is, and it starts pulling more mass in. But as it falls in towards these clouds, it starts to spin. And that spins it into a disk. Here's another one. This is the Orion Nebula. They're beautiful, and the reason we can see them is usually you can't see the clouds in visible light because they're dark. But when there's stars inside it, the stars then light up the cloud from the inside, and that's what we see. And so this is in the Orion Nebula. There's something called the trapezium in here, where there's these really bright hot O stars that are lighting up the whole cloud, and that's why we see it. Okay? Now, so we think that all the cloud falls in, and like water going down a drain in a bathtub, it spins, and it spins into a flat disk. In the disk, in the center of the disk, 90% of the matter goes to the center of the disk. That's what's going to form the star. But in the material out of the disk is where the planets form. So, how do we test that? Well, we look for these disks in these giant molecular clouds where stars are being formed, exactly what we expected when our solar system formed, and that's what we see. These are disks of material as these stars are being formed. Here's a closer up view of it. You can see this is disks. These are disks too. This is material falling in, spinning into a disk. Not stars yet. It takes a while for that matter in the center, all that gas and dust has to compress together, and it compresses together enough until the core gets hot enough. Once the core is hot enough, you get thermonuclear fusion and you form a star. And then out of the spinning disk, you have all this material orbiting around, but it keeps running into each other, and over time it builds up, and these chunks get bigger and bigger, and they essentially sweep up all the material around them, and they become the planets. That's the current view of how it works. Here are these, what we call protoplanetary disks. Before they're planets, remember proto is before they're planets, this is the disks. And we see this, these are in that Orion Nebula cloud, giant molecular cloud that I was showing you. So that's why we're pretty sure we understand how the solar system was formed, because it matches exactly what we expected, and we see this happening in other places in the galaxy. Also, we know that, remember, that all the material, all the planets, all go around the sun the same way. They're all going counterclockwise. Okay? And they all rotate counterclockwise with a couple exceptions. I'll explain those in a little while here when we get to each of the planets. And so the whole cloud we know that it formed out was spinning counterclockwise, and the reason that all the planets are in the same plane because they were in that same disk. If it was just chunks of planets floating around and the sun happened to capture it by their gravity, they would be going in all different weird orbits. But since they're all in the same plane, they were all formed at the same time. This is an artist's rendition of what it was like. You start to get these chunks or rocks, then the rocks start to come together and they get bigger. Now the reason planets all are spherical is because all those chunks coming together make it really hot, and they were liquid at one time. There's liquid magma. And that liquid magma then will pull itself into a spherical shape out in space. And that's why all planets or any large object that was ever liquid is going to be a spherical shape. Alright, here is another artist's rendition of what it would be like. The sun is going to form in the center, but in these outer rings of this gas cloud is where you start to form the planets, and then over millions of years, all that material will start to come together, and the bigger the chunk gets, the more it sweeps up more material, and they get bigger and bigger and bigger. Now what we see in our solar system, which we thought was the norm but we're not sure anymore, is that we see all the planets that were close to the sun are these rocky planets, right? Mercury, Venus, Earth, and Mars. They're rocks, they're chunks of rocks. Okay? Once you get beyond a certain distance, we get to the larger planets, what we call the Jovian planets, and they are mostly gas. Well, the reason for that is when you're in here, it's very, very hot. It's hard to get a large enough object to hold on to that gas, that light gas like the hydrogen and helium. So the Earth doesn't have enough gravity to hold on to that for the temperature that the gas is. But when you get far enough out in the solar system where it's colder, those planets could hold on to the hydrogen and helium, so that's why Jupiter had to get so big so quickly, is because it held on to that gas. All right, so now we're going to talk about the two different types of planets in our solar system. We have terrestrial planets, and we have what we call Jovian planets. Terrestrial means Earth. So a terrestrial planet are Earth-like planets. So terrestrial planets are Mercury, Venus, of course Earth, and Mars. And Jovian, remember Jove is just another name for Jupiter. These are Jupiter-like planets. So this is Jupiter, Saturn, Uranus, and Neptune. All right, so we notice that they have similar properties. The terrestrial planets all are close to the sun. They're small. They have high density, which means they're essentially chunks of rock and not gas, right? They have thin or no atmosphere. And they don't have rings. Now the Jovian planets have exactly the opposite. They're all far from the sun. They're large. All of them are larger than all of those. They're low density, which means they're mostly made of gas, not made of rock. They have thick atmospheres. In fact, most cases, they're almost all atmosphere. They may have a small rocky core at the center, but it's almost all atmosphere. And all of these have rings. Now, it's not required that way. In fact, it's possible for any planet to have rings. In fact, Earth and Mars may have had rings in the past. But we don't have rings now, obviously. And if you look at the terrestrial, Earth is actually the largest of the terrestrial planets, barely over Venus. But those are the properties of the terrestrial and Jovian planets. And we think the reason they form this way is because they form close to the sun. The reason these form this way is because they form far from the sun.